Hereby I open this academic ceremony in which Miguel Basset Sagarminaga will defend the academic thesis investigating the development of metabolic dysfunction-associated steatotic liver disease and insulin resistance. May I invite you to present a summary of your thesis and the conclusions.
Thank you. Dear committee, esteemed colleagues, friends, and family. Over the next 15 minutes, I will explain the research I have conducted within my dissertation entitled Investigating the Development of Metabolic Dysfunction-Associated Steatotic Liver Disease and Insulin Resistance. The prevalence of obesity has increased massively over the last 30 years. And this is mainly due to an increased consumption of Western foods in combination with a decrease in physical activity, which lead to increased deposition in fat and fat tissue. Fat is also sneaking into places it shouldn't, like our organs. When fat builds up in the liver excessively, it can lead to a condition called liver steatosis, or fatty liver. Liver steatosis is linked to scarring of the liver, inflammation, and also sometimes liver cancer. We here focus on fatty liver that is associated with metabolic dysfunction, called MASLD. MASLD requires the presence of other factors such as obesity, high blood glucose, diabetes, high blood pressure, or high cholesterol. Fatty liver is also linked to complications beyond the liver, such as coronary heart disease, type 2 diabetes, and cancer. Fatty liver is now the most widespread global chronic disease, affecting over 30% of adults. We therefore really need to find ways to prevent it and treat it. To do so, my PhD work had two main aims. Firstly, to better understand the relationship between diet and liver fat accumulation. And secondly, to better understand how liver fat relates to other metabolic disturbances, such as insulin resistance. For the first part, we were interested in the effect of diet on liver fat. More specifically, the effect of diet quality. We wanted to see if the quality of the carbohydrates and the types of fat we consume matters for liver fat accumulation. Carbs are often categorized into two types, fast and slow carbs. Your fast carbs have a high glycemic index, they get absorbed more quickly and leads to greater spikes in blood glucose. They're often thought to be less healthy than slower carbs that absorb more slowly and leads to less peaks in blood glucose. In terms of fats, you may have heard of saturated fats, which are found in your dairy products and animal fats, and that are often thought to be linked to cardiovascular disease and other complications. So often seen as your unhealthy fats. And then you have your unsaturated fats, which are found in olive oil and avocados and salmon, for example, which are often associated with less inflammation and healthier outcomes. Typical Western diets are a combination of both high glycemic index foods and high saturated fats. So here we wanted to look at the effect of the combination of the two on liver fat content. To do so, we designed a diet, a study where participants would not lose or gain weight. Had a diet that is representative of a normal eating pattern. Think of a plate that you would normally eat with mostly carbohydrates, some fat, and also some protein. And the only difference between the two diets we wanted to compare was the type of carbohydrate and the type of fat in there. And this allows us to isolate the effect of the quality of these macronutrients. So I will be referring to the healthy diet as the slow carbs and unsaturated fat diet, and the unhealthy diet as the fast carbs and saturated fats. So then, in our study, we recruited 13 participants who were overweight but healthy, and between the ages of 45 and 75. We then asked them to follow both diets for 2 weeks each in random order. So some started with the unhealthy diet and some with the healthy diet. And we provided all the food products to them. At the end of each 2-week diet, we measured several outcomes. The main thing we were interested in was liver fat content, and we measured that through an MRI technique called MR spectroscopy. This technique also allows us to measure not only the fat content, but also the fat composition in the liver. Through MR spectroscopy, we also measured how much glucose is stored in the liver as what is called glycogen. We also wanted to know how much glucose is turned into fat in the liver, and we did that through heavy water, where the participant drank water with a tracer that is then incorporated into the newly made fats. And that allows us to track how much newly made fats there is. And additionally, we measured the effect of the both diets on glucose with a continuous glucose monitor. So what did we expect to happen? We expected that an unhealthy diet would lead to more accumulation of fat than the healthy diet. through several pathways. The first of which is the direct accumulation of saturated fats into the liver through chylomicron remnants and spillover. We also know that saturated fats lead to less fat being burned in the liver, so we expected that because less is burned, more accumulates. We know that fast carbs lead to greater spikes in blood glucose, and that would lead to more glucose being stored in the liver as glycogen, as well as more glucose being turned into new fats. All of these factors would lead to the unhealthy diet leading to more fat accumulation in the liver. And what we found was indeed that after 2 weeks of diet, liver fat content was much lower in the healthy diet when compared to the unhealthy diet. And that was really impressive in such a short amount of time, in 2 weeks, with no weight changes between the two diets, and also the total content of carbohydrates and fats in the diet was identical, just the quality changes. And this truly highlights that small changes in your dietary choices can make a huge difference for your liver content and, by extension, your metabolic health. So that's the main thing we were interested in. We wanted to see the effect of the diet on liver fat content, but we also wanted to better understand what pathways lead to this accumulation. With the continuous glucose monitor, we indeed saw that the unhealthy diet led to greater spikes in blood glucose. However, we did not find any effect on glycogen content or the making of new fats in the liver. And this is probably because we didn't provide them excess energy and not excess carbohydrates, which is known to lead to more fat being created in the liver. So overall, the takeaway from this first part is that small changes in your quality of carbs and fats in the diet can have a huge effect on liver fat. And fatty liver is quite invisible. It does not itself present many symptoms. But after years and decades, it can lead to metabolic complications. So swapping fast carbs to slow one and choosing unsaturated fats over saturated fats seemed like a good way to reduce it. So now that we explored the effects of diet on liver fat, we also wanted to better understand the link between liver fat and insulin resistance. Insulin resistance is when the body cells don't respond as well to insulin, making it harder to control your blood sugar levels. Your body works a little bit like a thermostat. It really wants to keep your blood glucose stable over time. If it goes too low, you might have issues, and if it goes too high as well. And the liver plays a huge role in this glucose control. When you're fasted, your blood glucose is low, so the liver, which has stored glucose, releases it to maintain your blood glucose levels stable enough. After a meal, you get glucose from the food, so your blood glucose increases, and your pancreas senses that and releases insulin. And the insulin then tells the liver to stop pumping out glucose and start taking it up. And that allows a tight control of your blood glucose. When you have a condition called insulin resistance, when after a meal your blood glucose increases, your pancreas releases insulin, but the insulin seems to be unable to tell the liver to pump out glucose, to stop pumping out glucose and to take it up. And that leads to hyperglycemia. And over the long term, that can lead to damage in blood vessels and kidneys, etc. So how do insulin resistance and liver fat relate? We know that with high liver fat, the ability of insulin to suppress the output of glucose is impaired. However, what we don't know is what happens to the glucose uptake. And that's what we wanted to investigate. And to do that, we first needed to figure out how to measure liver glucose uptake, to then investigate the relationship between liver fat and liver glucose uptake. One technique we can use to measure glucose uptake in tissue is called FDG PET. FDG is a radioactive tracer that acts like glucose that we can inject. It gets taken up by cells just like glucose is, but then it gets trapped. It doesn't get burned, it doesn't get stored, it just stays trapped. And because it accumulates in the cell and it's radioactive, we can detect it with a PET scanner. And this allows us to then generate images like this where we can actually quantify the uptake of glucose in tissue. This is often used, for example, in oncology because tumors use more glucose and then you can detect tumors, for example. What we then do is we combine this FDG PET with insulin infusion and glucose infusion to mimic somewhat what happens after a meal, where you have high blood glucose and high insulin. But we wanted to really do it in a control condition where we get to dictate how much glucose and how much insulin there is. Now that we had our technique, our main question was, does having higher liver fat mean that your glucose uptake is impaired in the liver? And to answer this, we recruited 15 people who were overweight and between the ages of 45 and 75. We recruited a range of liver fats, between 1% and 18%, and we assessed that with MR spectroscopy. And what we wanted to see is whether if you have low liver fat, you have a better glucose uptake compared to if you have higher liver fat. And then we did our insulin-stimulated PET to assess this glucose uptake in not only the liver, but in every tissue in the body. And what we found was that indeed, with higher liver fat, the ability of the liver to take up glucose was impaired. And this highlights clearly the link between glucose control and liver fat. People who had low liver fat had a better stimulation of glucose uptake in the liver when compared with people with higher liver fat. And this can potentially have big consequences for your blood glucose control and your overall future metabolic health. Beyond the liver, we also saw that other tissues were affected. We saw that with higher liver fat, your ability to take up glucose from your muscles was also impaired. And this further accentuates this hyperglycemia. And it goes to show that liver fat is associated to many impairments in metabolism that go beyond just the liver and affect also the muscle and fat tissue. So overall, the takeaway from the first part was that small changes in the diet can have a major impact on your liver fat content. And the pathways that lead to that still kind of need to be investigated further. And in the second part, we saw that liver glucose uptake was impaired with increased liver fat and insulin resistance. And now I give the word back to the pro-rector.
That's very quick. Thank you. We have a lot of time for the opposition. So the opposition will be opened by Professor Brouwers, who was the chair of the assessment committee of your thesis. He's professor of endocrinology and metabolic diseases at Maastricht University Medical Center. Professor Brouwers.
Thank you, Pro-Rector. So, dear candidate, before I start off with my questions, I first would like to congratulate you and also your team with a very nice result. I really, by the way, liked your lecture and very nice slides that you used. But I was very impressed while I was reading your thesis. You performed very nice intervention studies, and what I also liked is that you developed really state-of-the-art methods to non-invasively quantify hepatic glucose uptake, and I think that's very relevant in our field of better understanding metabolic diseases. So again, my congratulations on that. I would like to start off actually with the impact paragraph, with the end of your thesis, and actually almost with the last sentence of your thesis, page 140. There you say that, well, previous studies mainly focused on endogenous glucose production suppression as a measure of insulin resistance. Now you show that also aberrations in hepatic glucose uptake are relevant in MASLD. And then you say, well, we need to do more studies on interventions modulating hepatic glucose uptake. And I was really fascinated by that last part. What kind of interventions would you think of?
Highly esteemed opponent, thank you for your kind word and your question. In terms of interventions, anything that would be able to actually restore that switch that we see from the fasted state, where you have a net glucose output, to a net glucose uptake in the postprandial state. And the easiest answer would be that sometimes targeting a specific pathway is not necessarily the answer. Lifestyle interventions, for example, have a more overall effect on the body. So we know that weight loss can restore some of these pathways, or exercise, for example.
Mm-hmm. Okay.
So anything that would reduce, would improve insulin resistance overall and reduce adiposity.
Yeah, so that sounds reasonable and plausible, I guess. I'm a clinician, and you know, in daily practice, these kind of lifestyle interventions are not very, well, how to say that, sustainable or effective. So in the end, we need to use pharmacological treatment. Mm-hmm. So could you think of any pharmacological treatment to restore this balance, what you were talking of?
Yeah, so you have many options, and they all have their pros and cons, right? So you could have a glucokinase activator, for example, if you're interested in increasing that uptake. Depending on the condition, it might have the opposite effect you want, right? So if it contributes to increased fat accumulation, for example.
Yeah. So, well, that's really the point, I guess. So, because these drugs do exist, more or less, or at least they are in RCTs, they are being tested. They have not entered our daily practice yet. So what would you think? Would that be, because they are really being developed for patients with diabetes, because if you increase hepatic glucose uptake, well, your blood glucose lowers, so it's a perfect drug for people with diabetes. What do you think?
I think it depends on the condition, and I think I would want to increase that glucose uptake in the postprandial state, but not necessarily in the fasted state, of course. It could be an option, but then there might be some drawbacks, just like
yeah, so but now, so we have a patient who has diabetes, type 2 diabetes.
Yeah.
I think you know of that condition because that's what you studied. And now we give that drug. What would you think would be the net effect of that drug for that particular patient? So what would happen, I guess, that in the postprandial state, more glucose enters the liver. So that's good for the postprandial glucose peaks. So you have less glucose variability, just what you showed in your graph. But
then you have the downside that you're feeding the pathways, the lipogenic pathways, for example. Yeah.
So then you would have more liver fat.
They would have more liver fat, which could potentially lead to also more VLDL export and dyslipidemia.
Cardiovascular disease.
Cardiovascular disease, which is the biggest factor.
Perhaps liver failure.
Yeah.
Yes, yes. So I'm still wondering why these people are trying to develop these drugs. But
maybe in combination with other drugs, it could work. I think if you rev up maybe the metabolism of the liver with resmetirom or something like that, so thyroid agonist, then maybe if you siphon more glucose into the liver, but you also increase the metabolic rate of the liver, maybe then we'd have.
And the other way around, if you would decrease hepatic glucose uptake,
then you're protecting the liver from hepatic fat accumulation, but then you have hyperglycemia, so it needs to.
But we could give a drug, an SGLT2 inhibitor, to lose that drug via your urine.
No,
okay,
definitely.
So combinations of drugs, that in the end would be the fact, if we would go for drugs. And this also touches upon something what you found in your chapter 5. I was really puzzled by that. So you say increasing hepatic glucose uptake increases, I think that's what I concluded from what you said, de novo lipogenesis. Am I correct?
In some conditions, yeah, probably.
Yeah, okay. So in your chapter, I guess it was chapter 5, you found that, and that's also what you showed in your nice slides, that with increasing in intrahepatic lipid content, the amount of glucose that enters the liver decreases.
Yeah.
Yeah. I think in chapter 2 you gave a summary of different processes leading to intrahepatic lipid accumulation, and there you said that de novo lipogenesis was one of the processes that is increased in people with MASLD. Well, how to reconcile that? How to combine the fact that in people with MASLD there is a decreased hepatic glucose uptake, but there is more de novo lipogenesis. So how to explain that? I just don't understand that.
I think the fact that there's a decreased glucose uptake doesn't mean there's no glucose, right? And that DNL that we see often highly expressed in people with type 2 diabetes or with obesity has a lot of redundancies in its activation. So we have different transcription factors. We have the SRABP1, the CHRABP, and also mTOR. So there's a lot of redundancy that activate this, and it seems to be mostly
but still
hypercaloric.
Still there should be a substrate for that.
Yeah.
So these are the factors that regulate that. I totally agree with that. But still there should be a substrate, I would say glucose.
Yeah.
But apparently that enters the liver just less often or less than in people with low amounts of fat.
Yeah, it could be. Because also have to depend on glycogen stores levels and the mitochondrial capacity as well. So you see that starts to, the maximum mitochondrial capacity seems to dip beyond a certain amount of liver fat.
Okay, so you don't see it as a paradox. For me, it was really a paradox what I read. It felt contradictory. More de novo lipogenesis, but decreased input of glucose in the liver. But do you think, well, there could be... Or could it be, of course, de novo lipogenesis is not only derived from glucose? Are there other substrates that are responsible for increased de novo lipogenesis in people with MASLD?
Well, there's also fructose as well that feeds into it. It
Yes.
seems to be a more potent activator of it than glucose.
Mhm.
So that could be also a factor. I think it also depends on the methodology of those studies that have looked at DNL.
Yeah.
And here we have the samples, so we could analyze them.
Mhm.
Also upon hyperglycemia, hyperinsulinemia, which would be very interesting.
Yeah.
It depends on the conditions we measure it, and we see that a lot of those DNL studies use very hypercaloric diets or states of very high hyperglycemia and hyperinsulinemia. So those methodologies, we don't know in this study whether DNL was higher with people with higher liver fat.
Yeah.
Yeah.
Yeah. Okay.
It could be that a lot of the liver fat came from adipose tissue lipolysis, for
Yes.
example.
Okay, but on average, people with MASLD have more de novo lipogenesis.
Yeah.
So if you give people a standard meal, those with MASLD have more de novo lipogenesis than those without. Yes. So, and this is also what I wanted, you know, and you're the expert, so you should explain to me, because now I'm going to a field that's really not my expertise. But if I look at the way you perform the measurements of hepatic glucose uptake, you perform the hyperglycemic, hyperinsulinic, or hyperinsulinic hyperglycemic clamp. So your glucose infusion rate was different between the ones with high amounts of liver fat and the ones with low liver fat, I guess, because the ones with high liver fat were more insulin resistant. That's at least what I concluded from
Potentially.
table, what was it? Table 2, page 89. So could it be that those with high liver fat who had a lower glucose infusion rate because they were more insulin resistant in the liver and AGP and things like that, that you infuse less glucose, so there was also less glucose to be taken up by the liver?
It could be, but like what we see in the blood is that the blood glucose level was still very high at 10 millimoles. So the substrate availability for the liver was there.
Yes, but if you then compare that, I'm just filling the time, Prorector, but I'm finalizing. If you could compare that to the de novo lipogenesis measurement, there I think people get a fixed amount of calories. So the people with MASLD and the controls.
Yeah.
So perhaps my question is, what do you think what would have happened if you would have given fixed amounts of intravenous glucose? So not clamping on glucose, but just giving a fixed amount of glucose. What would have happened with hepatic glucose uptake between people with and without MASLD?
Well, because the main factor that seems to influence hepatic glucose uptake is that blood glucose level. If you have these differences in blood glucose level between participants, then that will affect your uptake. So that's
but that is daily practice, I would say, because people just eat. They don't say, I'm insulin resistant and therefore I take less glucose. They just eat a meal. Yeah.
So one of the aims of this study was mostly to set up a technique, and we wanted to do it like for the first step, to do it in very controlled conditions, to not also violate the parameters of like compartment modeling, for example, for the uptake of the liver. And it was much easier for first step to do it in a controlled way with a clamp. Of course, like as you know, like it's not the physiological route. We're not going through the portal vein, so that can induce differences. Yeah. So that was the first step. Then we can maybe look at more oral routes, an OGTT or a meal test, to have a more physiological way. But then you run into issues with your modeling. But,
I understand. Yeah. Really fascinating, and I enjoyed the discussion. I give the word back to the prorector.
Thank you, Professor Brouwers. The opposition will be continued by Professor Wagner, Professor of Diabetes and Metabolic Disease at the Heinrich Heine University in Düsseldorf. And Professor Wagner is present online. Go ahead.
Yes, thank you. Dear candidate, I also want to congratulate you and the team for this fascinating data. And it was also enlightening for me, and from several reasons. We are used to measuring organ-specific or deal with organ-specific insulin sensitivity, also in our clinical studies. But this technique opens new avenues to measure it in a fine-grained, in a highly organ-specific manner. And what I wanted to ask you, so if I look at the data which all makes sense. There's a discrepancy between whole body insulin sensitivity measured by the clamp and the glucose uptake by the myocardium. So normally higher insulin sensitive, liver fat content, higher liver fat content associates with lower insulin sensitivity, i.e. lower glucose uptake by the muscle, by the subcutaneous adipose tissue, but that was not the case for the myocardium. So if you could comment on this. So why does the myocard behave differently in this situation? That would be my first question.
Highly esteemed opponent, thank you for your kind words and your question. We were indeed quite puzzled by that as well. It's not necessarily what we expected. We might think of a few reasons why that was. It could be that there was more glucose available to be taken up by the myocardium in people who were more insulin resistant because it wasn't going into muscle or the liver. So that could be one explanation. And I think what is also likely is it depends on the segmentation of the myocardium. Depending how that's done, we see that there's differences between studies. If you only looked at, maybe you segmented it more into areas of more activity or less activity, that could induce some differences. There's a paper that did the similar protocol, so whole body insulin stimulated, but with euglycemia. And there, the people with type 2 also had a higher myocardium uptake. It was not significant, but you could see it in the KI that it was higher. I'm not sure exactly why. It could be more glucose is available. I don't know if it's insulin. It's not insulin dependent, probably. It's just the availability of this glucose for the myocardium.
Okay, I think as far as I know, there are all data showing that the myocard loves to eat fatty acids. So the fatty acids are like the default energy source for the myocard, and maybe this phenomenon you see here is an indication of a dysfunctional energy source adaptation by the myocardium in case of increased hepatic fat and increased whole body insulin resistance. So the energy source of the myocard is a special organ, special type of muscle, which also, if you think on physiology, this is a kind of muscle which has to work all your life, and it's not allowed for a myocard to make a longer break. So the physiological energy metabolism could be a little bit different from normal skeletal muscle.
Yeah, that's definitely the case, that it uses mostly free fatty acids. We seem to see that the more insulin-resistant participant also had higher free fatty acid levels. So then it's a bit, you'd expect the myocardium maybe to use more free fatty acids as well, but that then would say the opposite, right? So it's we were quite puzzled by it as well. Yeah.
I think there's a lot to discover here, but maybe there's an organ crosstalk which renders the myocard to behave differently with insulin resistance and do not use. So you are right. There's plenty of free fatty acids in insulin resistance swimming around in the plasma. Yet myocard is taking up more glucose, so not doesn't increase fatty acid consumption, but takes up more glucose. But so this is a very nice. This was a very nice like feature or new line of data which came from your results, which has to be maybe further evaluated upon in next steps. But I would also like to comment on maybe so doing these experiments which you did is extremely laborious, but we have to understand everything, how these organ-specific insulin sensitivities relate to diseases and relate to clinically relevant features. we have to look at this in a much larger group of persons. So did you think on ways to estimate these insulin sensitivities, like using indices? Do you know such indices we use in everyday clinical routine or in a routine of our clinical studies, many indices estimating insulin sensitivity? But do you think that we could also derive or generate indices to estimate this kind of organ-specific insulin sensitivities, which you measure with your FDG uptake?
Sorry, I didn't quite fully understand your question. Could you repeat?
Do you know the HOMA index? So the HOMA index is a simplification of insulin sensitivity, it covers mostly hepatic insulin sensitivity, although it's discussed if it's more whole body insulin sensitivity, but it's a kind of readout. So there are also other readouts, like you can compute the product of fasting insulin and fasting fatty acids, which would correlate with the adipose tissue insulin sensitivity. So it's a adipose IR, adipose tissue insulin resistance. And I was just wondering if you thought about making the next steps. So you're making in a small cohort, measuring a lot of things and deriving estimates or readouts to do this in a larger scale. So to measure these, to estimate these quantities, these features in much larger cohorts.
Yes, I think it could definitely be done. Of course, FDG is radioactive. We don't want to expose people to too much radiation for research. So having indices and markers of uptake would be a great advantage. So maybe a next step would be to validate some indices against the glucose uptake from insulin-stimulated PET. And then validate these markers. That could be interesting, yeah.
What could provide you further method from your experiments to do this? What do you think? So you have here, I very much like, sorry? Maybe only an echo, okay. So which I very much like is one of your studies, I'm not quite sure you did it in this same study. You also had CGM measures, continuous glucose monitoring.
Did in the diet study, yeah.
So in the diet study, so not in the PET, in this FDG PET study.
Not in the PET study.
It would be an interesting question if around from the behavior of the glucose curves after meals and doing test meals with CGM, you would be able to estimate insulin sensitivity and different kinds of insulin sensitivity in the body.
So this has been done previously with OGTT, so we could draw parallels with that, where OGTT, where they could 5.8 OGTT, where they could differentiate muscle and liver insulin resistance. So we could do the same with a CGM. Of course, the interstitial fluid has a different curve than the blood glucose. But yeah, it could definitely be investigated.
Okay. Can I interrupt you, Professor Wagner, because I'd like to continue with the next opponent, if you don't mind. Thank you.
Oh, thanks. I'm done. Yeah.
Thank you very much for your questions. The next opponent is Professor Coy, Professor of Medical Physics, especially vascular imaging at Maastricht University.
Thank you, Pro-Rector. Dear candidate, first I would like to congratulate you also with your wonderful thesis, and I would like to extend my congratulations to your promotion team. I was very impressed by the state-of-the-art techniques that you applied in your thesis to study fat accumulation in the liver. I have a few questions today on chapter 3. And first I was intrigued by the change in liver volume that you observed after the healthy diet. And you report the changes in the liver volume on page 40, on the second line. And I calculated the change in the liver volume based on these numbers. And it's actually, I find it quite large. It is actually a 5% decrease in liver volume after the healthy diet. So I wonder if you could explain why the liver volume changed. Because in the discussion you already say that this might be due to change in glycogen content, although these changes were smaller than you could detect with 13C MR spectroscopy, or alternatively it could be due to the change in fat percentage. However, it's quite a large change, 5%. How much glycogen do we have in the liver? How much fat do we have? Can such a decrease really result in such a large decrease in the volume?
Highly esteemed opponents, thank you for your kind words and your question. Indeed, that's quite a large change in as a percentage of liver volume. Some might be explained by hepatic glycogen changes, and some might be explained by liver fat, but not probably not 5%.
Yeah, because how much glycogen do we have normally in the liver?
About 100 or 150 grams, probably something like that. I think 200 grams.
Yeah, so total. Yeah,
total. So it's not, that would not account for that amount, probably.
Yeah, and what about the liver fat?
Well, let's say they have 5%, so it would be 5% of that. But that were not the changes we were seeing.
Yeah,
so.
because then all the fats should disappear, I think, to kind of explain this. So do you have any other thoughts about what could happen?
Well, we were not sure either. I think if it's not the water associated with the glycogen, or if it's not the fat, then we were not sure what it would be. Don't think it would be inflammation or something like that, or maybe it's the segmentation we did. But we were not sure exactly what it could be. Don't know if you have any ideas, but...
No, I just thought maybe indeed the water content changes.
Oh yeah, with the glycogen, No, of course,
but then this brings me also to the next question, because then, is the quantification of fat, is that still reliable? Because you use the water as a reference standard. Yeah,
because we use the water as a reference, internal reference.
Yeah.
So it could potentially affect it. We correct by weight, so maybe that corrects for it.
Yeah, but if you have less water, then...
If you have less water, then the proportion increases. But we still think our changes in liver fat were robust enough that we believed it were true changes and not affected by this water, hopefully.
Yeah. Okay. Yeah, I think, of course, 28% is a very large change.
Yeah.
So you would have to have a high change in water content, of course, to explain that. I agree with that, yeah. Also, I was looking at the results on the type of fats that you observe, and I noticed that it was really hard to measure it, and approximately half of the subjects you were unable to do it because of the problems with breathing artifacts and also low fat percentage in some of the subjects. So I wonder, do you have any thoughts about how these, the quality of the spectra could be improved for future studies to be able to measure this also in people with low fat percentage?
Yes, indeed. So now what we do is, if we're really interested in the liver fat composition, we try to avoid recruiting people with less than 2% liver fat, but that messes out on a lot of the population. So ways to optimize it. It's always a trade-off between the duration of the acquisition and the amount of acquisition, and between the signal and the duration. So increasing the acquisition could be an option.
Yeah.
Doing better respiratory motion control, so improving the protocol, improving the shimming and optimizing the protocol that we do.
Yeah.
Those could be all options.
Yes.
And also in the script, in the analysis, and the fitting, adjustments there. Yeah.
Yeah. Yeah, and I agree, of course, indeed, increasing the time of the acquisition, but and you also mentioned changing the protocol. And do you have any thoughts about, for example, what kind of changes in the MRI protocol could lead to more signal?
For example, better shimming, for example.
Yeah, you already mentioned.
Yeah.
But I mean, especially also the parameters of the scan and type of sequence that you use.
Yeah, I'm not exactly sure. I was not really involved in the development of them, so I don't know all the details. But yeah, I'm sure that adjusting the pulse sequence and specific for this population, maybe, or yeah.
Yeah, but of course, I fully understand that you mainly focus on the physiology. So I think I have still time for the last question, I guess. Yeah, and also about the 13C spectra. So I think that is like very challenging because you have not so much signal if you do 13C spectroscopy. So did you check the reliability of these measurements? So how reliable?
Yeah, so that was done before my time, but it was done.
Yeah.
They did retest. So they did the same participant went into the scanner, they measured the glycogen, then they went out of the scanner and redid it with the same position and saw if the results were similar, and there was a good coefficient of variation. Don't recall exactly the number, but it was pretty good, at least in retest within the same day. Here we have several weeks apart, but we try always to use the same position. We have we have markers on the coil to know exactly which position. So we between one intervention and the other, we place it in the same exact same position. So hopefully that improves that as well, the reliability.
Okay, thank you very much. I'm pleased with my answer, and I would like to give the word back to the pro-rector.
Thank you, Professor Kooi. The opposition will be continued by Professor Staals, Professor of Pharmacology at the University of Lille in France, and he's present online. Professor Staals.
Thank you very much. Dear candidate, I would like to join the other committee members by congratulating you for having performed very elegant studies in the context of an excellent team in Maastricht and using state-of-the-art technical developments, and you have highly contributed to that. So congratulations for that. Now I would like to come back to chapter 3 and your study where you have been comparing the impact of high versus low glycemic index saturated fatty acid diets on liver fat, where you showed the effects of the low GI SFA diets on liver fat, even in an isocaloric diet environment. Now, as a molecular biologist that I am, I'm a little bit, I would say, more interested in the exact components of the diet rather than talking about pasta and rice. I'd rather talk about fructose, glucose, and saturated versus unsaturated fatty acids, or proteins, amino acids. And so I would like you to tell me, because I was looking through your manuscript and the thesis, and I couldn't find a detailed table on the exact composition of the diets. And so I was wondering what components, molecular components, are different in fat, carbohydrate, maybe protein composition. I know the protein was controlled for, but have you any idea about what might be the real molecular differences? Of course, not in detail if you've not measured it, but in order to have an idea what might explain the results you obtain.
Highly esteemed opponent, thank you for your kind words and your question. Yes, indeed, we didn't provide the details here. In terms of saturated fats, the low saturated fat diet at 5% and the other one 15%. And the rest was MUFAs and PUFAs. I don't recall exactly the percentages here. And for the glycemic index, that's 1 point as well. The high glycemic index diet had on average a glycemic index of 60, whereas the other one around 30, if I recall correctly. So 60 is not, well, it's more like a medium to high glycemic index rather than high glycemic index. There was more fibers, of course, we couldn't avoid that. There was more fiber in the low glycemic index diet as compared to the other one.
So then, would you speculate on the action mechanisms on de novo lipogenesis and liver fat? You mentioned, for instance, the fibers, and that impacts. I wasn't even thinking of that, but now you mentioned it, it would impact also the gut and the microbiota that can contribute to a certain extent. But globally, what do you think is happening from a mechanistic viewpoint? Is there a difference in glucose versus fructose, which I think you've already studied also in other studies, the fatty acid composition, or what is your idea about what's happening, the mechanism?
Potentially, in terms of fatty acids, so we know that saturated fatty acids increase de novo lipogenesis, increase adipose tissue lipolysis. There could be a lot of free fatty acids coming from adipose tissue contributing to that liver fat accumulation. Increases.
Have you measured those?
Sorry?
Have you measured the free fatty acids in?
Yeah, unfortunately, we didn't measure those. No. Yeah. That's something that's missing. We're missing part of the story there, unfortunately. There could be effects of the saturation of fat on fat oxidation. Saturated fats leading to less fat being oxidized specifically in the liver. We measured whole body fat oxidation, but not specifically in the liver. And then we know that MUFAs improve triglyceride clearance, for example, in the bloodstream. That might have some effect. In terms of GI, we expected that the high GI would lead to peaks in glucose and insulin, and that leading to more glycogen being stored in the liver. We measured it only in the fasted state, so we didn't see any effects. In hindsight, it would have been good to measure it postprandially, maybe 4 hours after the meal test, to see if there was an effect of the two diets on glycogen content. And we did measure the postprandial DNL, and there we failed to see any effects. Probably because it was a isocaloric diet, and typically DNL we see effects when we give a high carbohydrate load. Visually, it looks like it's a little bit higher. But we're actually in the low diet, so we don't know yet. I don't know if there would be an effect. There was an effect from fasted to postprandial, but.
So one parameter that I don't think you didn't allude to, that's associated with hepatic steatosis, based also on the genetics of the few genes like TM6SF2 and MBOAT have been identified to precipitate steatosis in patients, is the output of VLDL, and so the production of triglycerides to the plasma compartment. Have you looked at the plasma lipid levels and lipoprotein levels in these patients? You didn't look at the free fatty acids, but maybe you looked at other lipid parameters. Could that be? And have you done a genotyping of your patients?
Well, we did see on our control day before the meal test in the fasted state, there was a difference in total triglyceride in the blood with lower triglycerides in the low GI diet. This difference was also in the postprandial state. There's probably potentially effects on VLDL export or also triglyceride clearance, so LPL activity, for example.
So it's complicated to conclude because it could be both an impact on export and on clearance, so it's difficult to assess that. And any genetic markers measured like PNPLA3 or MBOT? I know it's a small group of
Yeah. Maybe we should have, we didn't measure anything. Yeah, we know that PLA3 is quite sensitive to changes in diet and changes in energy, and that unsaturated fats might inhibit it quite potently, and that it's associated with increased liver fat accumulation when it's active. So that could have definitely been a factor. We didn't look at it there. We focused more on the other factors, but we could have definitely measured that. Yeah.
And another difference that can happen with saturated versus unsaturated fats are the impact on the immune inflammatory system. And that happens in immune cells in the liver, also in the circulation. Any ideas about this? Anything that you measured to assess this aspect?
No, we didn't measure it. It could have definitely been interesting, especially we know that lipid synthesis intermediates like DAGs and ceramides and long-chain fatty acids cause also inflammation and impairments in insulin sensitivity. So it would have definitely been interesting to measure some inflammatory markers. However, we did not here yet. No.
Okay. I don't know if I still have time for a question.
Only if it's a very short question with a very short answer.
That would be difficult. So maybe I'll hand over the.
I think so. Okay. Thank you very much, Professor Staels. Yeah. Then we go to the last opponent, Dr. Mitea, nuclear medicine doctor at the Maastricht University Medical Center.
Thank you. First, I want to start with congratulating you with the book and with the nice results, and also your promotion team. And I want to talk about one of your propositions. So I would ask you or one of your paranames to read number 5, please.
Go ahead.
Dose reduction in PET is essential to apply PET broadly in metabolic research.
Thank you. And then if we would look at chapter 6, so you focused on the reduction of dose or radiation dose for not patients, but for your test patients. Okay. And you only looked at reduction of the doses of the FDG. And you said, okay, one of part of the radiation is due to the FDG, and the other one is to the CT. Yeah. And did you thought about using a different technique, like a PET-MR, instead of a PET-CT?
Esteemed opponent, thank you for your kind words and your question. Yes, so here we focused on the FDG. It's very site-specific. This last chapter is very relevant for us as a group and maybe as MUMC and Maastricht University. It might not be so applicable to other situations. The specific situation here was we were more confident on the image quality of the PET-CT at MUMC as compared to the PET-MR, which is a bit older. And that might not be the case everywhere. Of course, if we do PET-MR, we don't have the radiation from the CT, which would be advantageous. Additionally, maybe potentially we could use MR spectroscopy coils to measure other things, maybe like glycogen uptake or things like that. So that would be very advantageous. Here we focused on the FDG. It was more in the optic of, let's do this whole body dynamic protocol. Can we do repeated measures, for example? The only study that had done this type of protocol with insulin stimulation was in Sweden, Antaros. And they had used 4 megabecquerels per kilogram. So we wanted to first figure out, we didn't want to take the risk with a lower dose right away and take the risk of having a bad image quality. We have very large volumes of interest, so it should be fine. So what we did, we first recruited 3 participants, and we gave them 4 megabecquerels per kilo. Then we assessed the image quality subjectively and also the SNR. And we established that we could reduce it potentially by half. We did a partial reconstruction. Yes. We could reduce it by half, but we didn't want to take the risk, so we went to 3 megabecquerels.
Yes.
And then, yeah.
Okay, thank you. My next question would be about chapter 5. If we're going to page 89 on table 2, if I understand it correctly, you do not see any difference in the glucose. The glucose does not increase in test patients with different amount of liver fat. Do you understand it correctly? And do you, is there a reason? So if you're looking at SAT, so subcutaneous fat, and you don't see any difference between the lower liver fat, medium liver fat, and high liver fat in the accumulation in the glucose uptake.
Indeed, it stayed quite stable.
Yes.
Yeah.
Can you comment on that? Because I was, is it like an inert organ? We do not need it?
Yeah, I think it's definitely not inert. I think we show that it's a quite active organ with also adipokines, etc. But yeah, it seems to just be pretty steady. I compared it. I think on one table you can also see comparison to other studies, and the Ki is pretty much the same. It seems to stay pretty much at a steady glucose uptake. Maybe it's because it's not saturated. The uptake is not saturated, or it's just not very avid for glucose as well, so maybe it just stays there. Yeah.
Did you thought about looking at a visceral fat, because that could be more active?
Yeah, we were discussing it. I think the segmentation was a bit challenging in our images, so we didn't specifically look at it. We had consortium partners that do it with automatic segmentations, and then it's much easier. With manual segmentation, we didn't look at it, but we still have the data, so we could always look at it. Okay. There could be some differences. I think some studies, I think from Turku, showed differences between visceral fat uptake and yeah.
That's right. And now, so you probably know this is like me as a nuclear medicine doctor. I'm focusing on imaging of cancer patients. You also said in your presentation we can use it to detect accumulation in metastases. So I was curious, do you think that the results of your research would influence the way that we're looking at PET? Because the cancer patients, they also many times are having like steatosis, hepatitis. So what are the consequences of your research on evaluation of PET? And I'm thinking the time that we take the images, we're looking like 1 hour after the injection. We're looking at the SUV measurements. You're looking at something else. So can you, I'm curious about your thoughts about this.
There can definitely be applications, because the advantage is that you can quantify. So it's not like SUV. Yeah, it's a good measure, but here we can quantify uptake. It might be advantageous for some settings. There was a review by Ramim discussing whole body scans, and they said that's for so smaller lesions and smaller tumors. Sometimes you might miss them because you're not spending your whole time in one bed position. You're moving through the body, and with changes in movements, you might miss the lesion. And they saw, for example, on the bladder, which expands potentially expands throughout the scan, that they would miss the lesion with dynamic scanning, but they would see it in the SUV. So it's a bit of it depends what you're looking at. Definitely if there's metastasis, a whole body protocol would be very interesting. Also anything looking at, for example, the gut-brain axis and things like that, where there's multiple organs involved, it could be useful. I know that some of your colleagues are using this protocol to look at cancer patients. And they're inviting them to, they have their regular clinic scan with the SUV, but they add the dynamic scan before that, the dynamic whole body. It could be interesting. I think maybe it could aid, for example, AI in the future if you have you quantify the uptake, maybe a numerical input of uptake. Maybe AI can detect something that we cannot detect by eye or by our expertise. So, yeah. And
now, then I want to make a connection between my second question and this question. So the SUV is a measure of the FDG accumulation in the whole body. Okay.
Well, you continue the discussion later on. Thank you very much, Dr. Mitea. Jeremy Basset Sagarminaga, the time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return in this room.
Thank you.
All right, please.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Southside, 7 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Take the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. And even though these nights seem long, I know that I am never on my own. Know you won the battle once you've grown. Southside, 7 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goals only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile.
Miguel Basset Sagarminaga. The degree committee here present has assessed the quality of your thesis and of your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Schouwe-Hindeling is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite your supervisor to now take the floor.
All right, please.
Do you promise to work, so I will ask you, do you promise to work in accordance with the principle of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible? I promise. By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon Jeremy Miguel Basset Sagarminaga the degree of doctor and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee and affixed with the official seal of the university. So, dear Dr. Basset Sagarminaga, dear Jeremy, it is my great honor to be the first to congratulate you with your well-deserved doctor title. I do so also on behalf of your co-promoters, Patrick Schrouwen and Tineke van der Weijer, and of course also on behalf of many of your colleagues who have worked with you in the last 5 years. I would also like to extend my congratulations to your girlfriend, family, and friends. It is indeed more than 5 years ago when we were looking for several PhD students in the group. I think you actually applied originally for another position, which was already filled. But you had an interesting CV, and I was also in need for a PhD student on my ERC grant. You had performed an internship with Wouter van Marken-Lichtenbelt, and he was very positive on how you performed. And as you made a good, serious impression, you seemed genuinely interested in science, I contacted you with also this project, where we wanted to focus on applying imaging methods on the liver, seemed interesting for you. You were indeed interested, and we hired you, and I'm very happy with it. In a laudatio, we generally look back on a PhD period and review how things went, pointing out some characteristic and maybe funny things that happened. I must say that it was not so easy to write this laudatio, because my experience with you is that you were always very to the point, never providing more than necessary information. Meetings with you were mostly short. Nothing superfluous was discussed. Always very professional and very well organized. It is not very often that when you ask something as a supervisor that you get more back than you expect. When I ask people to check in the literature, this is often something that is done with a bit of resistance, for example, and mostly performed marginally. However, when I ask you to check the literature, you did not come back with 1 or 2 papers, but with at least 4 or 5. When we needed to write a rebuttal, you already came to the meeting with a well-formulated suggestions. You did things very thoroughly and proactive. This is also what I heard back from Tineke. You prepared everything well in advance and always organized double or triple backups for any material. This good preparation and organizing everything well in advance was not only something that you did for meetings, so also for measurements, you prepared everything very well and also well in advance. In fact, it may have been a bit too much. Colleagues who also wanted to use the experimental rooms at the MROM had to navigate between your preparations that you have set up 3 days before the test day. This also matched my experience with you in finalizing the thesis. I never had to remind you of anything. No matter whether it was propositions, the lay person's presentation, you already had a plan prepared and discussed, and you stick to the plan, and everything was well on time. So, Jeremy is the most serious and most precise person on earth. Can that be true? I also inquired amongst your colleagues. Well, they did not completely agree with my image of you. It became apparent that the serious Jeremy that I knew also had another side, quite well hidden from me. So it seems that you also like to have a bit of fun at work, meticulously following up on any inside jokes and placing photos and other stuff among the documents of colleagues so that they think of you with a smile any time of their working day. So there is certainly another Jeremy, and we may hear more about that later today. But like myself, also your colleagues mentioned that you are a colleague that you can call on and really rely on any time. It is clear that you are a person of many talents. Your sports achievements are incredible, and I could see the ease with which you are running when we had a group day on the Petersburg. We were dispersed in various groups, and there was an athlete running towards us. He went super fast. And then I suddenly realized, hey, this is Jeremy. You coordinated different groups and needed to be fast, going from one group to the other, so you just ran, and really, really fast. I was impressed. You actually planned the finalization of your PhD around races in Abu Dhabi, Spain, and other places. And we had Zoom meetings from there to make sure that you were well on track with your schedule to finalize everything on time. To combine performing at the very highest European level in trail running with finalizing these things really show your discipline and organizational talent. The perseverance needed for such athletic performance you also showed during your PhD. Never give up on inclusion or on data analysis. You didn't give up during troubled times, nor during COVID. And the perseverance to finish your projects resulted in literally pushing the last test subject after the PET over the finish line that Tineke had installed for you. Also, your language skills are impressive. When you came to Maastricht, you mastered, next to English, also French and Spanish. Although you had learned Dutch to be able to communicate with the study participants, it was for a long time not clear to me how good your Dutch actually was, because we went on talking English. In fact, much longer than would have been necessary. I think you also had pleasure in learning Dutch. And it seems that especially the fact that you can make things smaller by adding a j appealed to you. Everything was turned into diminutive. A clamp became a klampje, and you had fun taking it all the way to a GCM'tje and glycogeentje. Jeremy, you are really a team player, bringing dedication and positivity to work. And I'm very happy that you found a new challenge in an interesting position at Medtronic. I think they can really be happy to have you. In Dutch, we would say, ze mogen in hun handen, ik bedoel, in hun handjes, knijpen. Dear Jeremy, you performed your thesis in a very difficult time. First COVID, and then the terrible troubles at the university that hit your supervisory team very hard and diminished our research group. Nevertheless, you succeeded in finalizing your PhD nicely, which is really a big achievement you can be proud of. And I know that I say this also on behalf of your other supervisors, Patrick and Tineke. And with this, I would like to give the word back to the prorector.
Yeah, dear Dr. Basset Sagarminaga, also on behalf of Maastricht University, I congratulate you with the degree you have acquired. I also congratulate your family, friends and colleagues who have somehow supported you during your PhD trajectory. I'd like to congratulate your supervisors, and thanks to the members of the degree committee for the work they did for this PhD defense and their presence here, and online, especially our guests from abroad, Professor Wagner from Germany and Professor Staals from France. Thank you very much for your contribution. I can tell you that the committee was very happy with the way you defended your thesis. We enjoyed your late presentation. It was very clear, and we enjoyed the slides. But you also, about defending your thesis, you showed that you have expertise both in the physiological topics and in the more technical aspects, and that's really a very important combination, I think. I hope you also feel satisfied with the way you defended your thesis, and it's now time to enjoy the fact that you were given the doctorate from this university, and with this I close this academic ceremony.